For when we try to solve stress analysis problems, we never get standalone model. Okay, we always get assemblies. So there will be a lot of complex assemblies involved in the model. So the interfaces of these assemblies, we can use uh, several methods to connect these interfaces. So some of the couplings and CS majorly it will have interpolation between the mm, between interface components. So when they are trying to couple together, or when they are tied using CS or couplings, so most of the things are linear interpolation. Okay. So whereas in context we can go when we give context, certainly there will be nonlinear interpolation. So that is more realistic and accurate simulation. So yesterday we looked into various types of advantages of constraint equations and couplings. So couplings basically requires no coincident nodes. So we cannot give couplings for dissimilar meshes. So certainly we can use only coincident nodes with same mesh element types. Suppose if I have a component like suppose when we are trying to do one analysis. So this is a solid, and this is a shell. So the basic difference between solid elements and shell elements, solid, each node will have 3 degrees of freedom. Shell will have 6 degrees of freedom. So 3 are US, translation UY, UZ, and 6 degrees of freedom are US, UY, UZ, also rotate, rotate, rotate. So when you try to tie these two elements at the interface location, you cannot use CPs because CPs using CPs we can tie only rotation, translation. So we cannot tie for rotation. So generally it is not advisable to use. Couplings are not advisable to use when there are dissimilar element types. So this is shell element, this is solid element. Sometimes solid elements are tied with beam elements. Okay. So suppose this is the beam element. Okay. So we need to tie here. So you cannot use couplings here. So for this type of things, we can go for constraint equations. So here we discussed about how the interface areas we match the mesh pattern, and then we used couplings. This is also related to how the mesh is matched at the interface location. So when you give couplings, then see the displacement pattern. So at the interface location, there is no change. It is smooth gradient exists, similar to other locations. So if you see here, the deflection at the coincident nodes is same. That means what it says is the deflection at one point when their two nodes are coupled, the deflection is solved for one node and it will be imposed onto the other nodes. Yesterday we discussed on that. So here we have used couplings. Okay. These two these two components are tied at this location. This is CP. Okay. So as per our finite element as equals to Ku, when there are no constraints, this K will be singular. So let us take this component 1. So this component is constrained here. So stiffness matrix of this one A is non-singular. Singularity is removed. Okay. So but here it is not constrained. Okay. Then K is a singular. Okay. But this singularity can be avoided if you try to establish or if you try to get some connectivity from this boundary condition to this one. So that that relation we can establish by tying this interface with either Cs or Cs. Give me 1 minute. So, the singularity can be avoided if you can establish some relation for this component from this component. So we can get some this deflection we are getting it we are constraining here. So the constraint can be established as a relation. So the relation can be established through couplings here. Okay. So couplings are constraint equations. So constraints if we apply to only master nodes. Okay. Constraints equations are used for variety applications, connecting dissimilar meshes, modeling interference fits, connecting meshes that have different degrees of freedom, that is connecting shell and brick elements, and modeling rigid regions. So one of the example is connecting components with the dissimilar meshes. So here if you see here, this part is brick mesh, this part is pet mesh. Definitely we cannot establish any constraint mesh here. So here we need to go definitely with constraint equation. So we have used constraint equation and we solved the problem. So with couplings and with constraint equations, we are not seeing much difference here. So couplings used coincident mesh, and here we have used dissimilar mesh between these two parts. And we are seeing there is no much difference in the deflection. So couplings and constraints equations are act like elements in that they increase the connectivity of the finite element model and therefore increase the bandwidth or wavefront of the system. That what does it mean is like if you use couplings and constraint equation, definitely the problem size will be increased. At the same time, computational effort will also increase. So in constraint equations, generally the degrees of freedom we establish a relations between the nodes. In couplings, degrees of freedoms we ensure that if you try to establish a relation between this node using CC, we'll say that deflection here and deflection here will be same. Deflection here same, here same, here same. So we are imposing that this deflection of this node should be same as deflection of this node. Okay, that is called coupling. CC. Whereas in CE we will establish relation between these two things. That we'll discuss. And in multi-point constraints, we won't define any equations, but it's like equations, we won't write any equations, but they will be created while solving. So we already discussed about nodal coordinate system. We can have like by default Cartesian coordinate system for all the nodes, or we can change it to specific coordinate system. And this coordinate system I hope you are unable to see my desktop. Okay. So, this nodal coordinate system is very critical for cyclic symmetry analysis and other type of stress analysis. So it is very important for you people to understand how to see the how to give that nodal coordinate system while assigning boundary conditions. So some of the examples, some of the things, some of the information again on couplings. So common applications will be enforcing symmetry, frictionless interfaces, pin joints, to model sliding at the blade and disc interface. So this is one of the example enforcing symmetry. This is our 360 degrees model. So instead of solving 360 degrees, we can take a simple sector model, and this sector model we can enforce the symmetry by coupling at the cut faces. So all these nodes at the cut face need to be rotated in cylindrical coordinate system, and then these cut face nodes need to be coupled in 3 degrees of freedom. So let us discuss about this problem. So this is a one of the representative thing of a disk. Generally, disk is comprised of blades. So we have taken the disk with holes here. So what we have done is we have taken around 30 bolt holes here, and um, we model both hollow. It's a hollow disk. So here we can use two techniques. One is 360 degrees model and cyclic symmetric model. So as we discussed in some time back, 360 degrees model we can consider only if our loads are not uniform throughout 360 degrees. So suppose if disk is subjected to rotation, if disk is subjected to rotation or angular velocity, so we can so this will be subjected to uniform throughout the okay. So for this type of thing, we can take a simple sector model. No need to analyze complete 360 degrees model. Suppose if you are having a loading pattern which is varying throughout 360 degrees. Here we are zero loading, but here we are having peak loading. Then in this type of model, we cannot use sector model. We need to use 360 degrees model because load is varying, and highest loading will be happening at this location. So definitely we cannot use sector model. So in this example, disk is subjected to 1000. Generally, most of the aero engine applications disks are subjected to uniform loading throughout the 360 degrees. And since blades will be there, we will take a simple sector model. So here for this problem, disk is subjected to angular velocity 1000 rpm. So simple sector cyclic sector is sufficient. So here the constraint, as we discussed earlier, we have constraint 4 nodes, 90 degrees apart, okay, in axial and circumferential direction. So what we did is we selected these nodes, rotated in cylindrical coordinate system. That means cylindrical coordinate system is we selected this node. So cylindrical coordinate system. So radial will be this direction, O, and axial will be into the plane. So this is the radial, this is O of theta. This is theta. Similarly for here, radial is this direction and this is theta. So radial is this direction and theta. So radial is this direction and theta. Okay. So theta is always tangential to the nodes. Okay. So we need to constraint theta or hoop. We'll also call it as hoop and axial. That is the axial. So these are the constraints we need to give on this problem. So then what we did is we have taken a sector that is a 360 degrees. These boundary conditions are related to 360 degrees. So then next step is this is one type of approach. Then we worked on cyclic symmetry, enforcing symmetry, cyclic symmetry. Basically what we did is we have taken these two cut faces. We ensured that the mesh pattern on this face is same as this face, so that we can give couplings between these two faces. So we enforce we ensure that these two faces are coupled. Okay. What does it mean is the node at this location is exactly coupled at this location. So node at this location are coupled in 3 degrees of freedom. So what is the change here? So if you list this node in cylindrical coordinate system, node 1, X, Y, and Z. This is 1. This is 2. Node 2. X1, X2, Y2, Z2. So the difference between coordinates, okay, in cylindrical coordinates, these are the cylindrical coordinates. So basically the difference will be this and this will be same, this and this will be same. So only change will be theta. Okay, y1 and y2 will be changed. How much is the change? Is y1 minus y2 should be theta. Means the angle between the sector. So remaining things should be same. So all the nodes here, surface, there won't be any difference between radial and axial location. Only change should be in the hoop location. I hope it is very clear for you. If you have any questions, you can raise. This is very important topic and very important in terms of analysis of rotors, okay, or flywheels. So and also so this and this will be same, and this and this will be same. Radial location same, z location same, and theta 1, theta 2 should be different. So theta 1 minus theta 2 should give theta, that is angle, sector angle. Okay. So all the nodes at this surface should be same. Okay. So only difference should be theta. And one node here is constraining in theta and z location to avoid rigid body motion. So one node will constrain in axial and hoop direction. So when we try to solve this both 360 degrees model and cyclic sector model, if you see the deflection plot, there is no change. It remains same. Since it is subjected to angular velocity, definitely there will be a radial growth. And the loading will be more at this inner core. So definitely there will be radial growth more at this location. So if you see here the stresses, we got 185 KSI or 185 MPa. Yeah, 185 KSI, it is in KSI. So, and we observe basically at the whole location. So here also we observed basically at the whole location. If you see here, the stress pattern remains same. There is no change at all, and the even magnitude remains same. What does we conclude? Instead of modeling 360 degrees, go for cyclic symmetry and capture the geometry properly and do the analysis. This is the smart technique. So any questions on this case study, just let me know. Otherwise, we'll go for next topic. Okay. So and this is coming to couplings. Again, a contact surface can be simulated using coupled degrees of freedom if all the following are true. Sometimes, as we mentioned earlier, instead of contacts, we also go for a coupling. Suppose if you see here this example, bolt and nut. So bolt and nut, we can use couplings here. So only thing is our assumption should be the surface will remain in contact, whatever may be the condition. So when you try to give couplings at these locations, what we are enforcing them is they should be always together. And other thing is analysis is geometrically linear. Okay, so we cannot capture in non-linearity at this location. Friction will be neglected. There won't be any frictional forces. Node patterns should be shown. So these are the some of the things on frictional interfaces simulation. So some of the assumptions we have to consider. Suppose coming to couplings in joints, constrain some degrees of freedom and leave other free. So this is used to couplings are also used to simulate the joints, and when there is suppose instead of in this example instead of coupling all degrees of freedom, we are coupling only ux and uy and leaving rho z. So some of the cases we need to omit some of the degrees of freedom in coupling. That we will be doing it. We can do it in using couplings. And one of the important thing in couplings is we can simulate bladed disc interface. Nowadays, most of the time we are using contacts. We are not using couplings. So, but our area of interest is not at this location, at this critical location. This is very critical location. Is this bladed disc. Okay. So even sometimes to get faster and then instead of contacts, we can go for couplings as well. So here nodal coordinate system of the disc and blades can be rotated to the tangent and the normal to the interface. Basically, this is typically we'll call it as a poetry or blade attachment tree. So here, so what we need to do is these nodes where the blade is contacting the disc at this location, so we need to rotate the node, tangent and normal. Okay, so we need to rotate the nodes tangent normal to the surface. So this is the surface. So we need to rotate the node tangent and normal to the surface, and then couple the nodes in normal direction. So in this direction, we need to couple all the nodes on the blade and the disc. Okay, at this location. So all the nodes at the interface are coupled normal to the uh, interface location. So here, so this will ensure that there will be frictionless sliding. That means we are arresting only normal directions. We are not arresting along this direction. So this blade is free to move along the side along the blade attachment region. So it can move in and out. Okay, but it cannot move out. Okay, okay. Radially, blade cannot move out, but it can slide. So this is one of the applications on couplings. So as we mentioned, like constraint equations are mainly used to establish relations between the nodes. So generally, like in coupling, what they are telling is node 1. So node 1 US1 equals to US2. This is called CB. Whereas in coupling, we will establish a relation between these two things, US1 plus some factor US2 equal to say some constant. So this is called series. So in CT it is straightforward, both definitions are same, but in CS we will establish here. General form we can give it here. Like this you can use this equation to establish relations between among several nodes. So I am telling only two nodes. We can establish this relations for several nodes. It may be 1, 3, 4. Okay, so many nodes we can establish the relation in similar fashion. Depends upon our analysis requirements. So common applications are like connecting dissimilar meshes, um, connecting dissimilar element types, creating rigid regions, providing interference fields. So these are some applications in constraint equations. So one of the things is connecting dissimilar meshes. So if you want to establish a relation between these two things, if you see here, there is no connection between these two components. This is having perfect mapped mesh and this is having free mesh. The interface, it doesn't have any common mesh here. So in this type of things, like we can use CS to connect dissimilar meshes. Similarly, in the similar example, like I have a model here and shell model here, and if you want to establish connection between these two things, we can use CS. So same is the case for beams and solids. Beams to solids or beams perpendicular to shells, shells to solids. These are some examples. Where so here you need to understand like we can connect dissimilar meshes only through series. So some of the things on constraint equations, we are used to also used to create rigid regions. So let us understand what exactly rigid regions. So generally in ANSYS we'll call it a CERIG or RB2 in NASTRAN. So here we use one master node and several slave nodes. The degrees of freedom affected should be included in the Cs. Okay. So here if you see this example, this is the master node. The remaining nodes are slave nodes. Basically, this master node will control the behavior of all these nodes. So it will give the necessary directions to the all the slave nodes. So generally, this master node, if it is not attached to any of the elements, this we need to create a mass element here, and we need to give a negligible mass to that, so that it will have some of the functions, element functions associated to that node. So basically, this CERIGs are used to apply boundary conditions or loads to the model. Okay. The master node contains the independent degrees of freedom, and the slave nodes contain dependent degrees of freedom. So this master node will have independent degrees of freedom. That means it will have degrees of freedom independent, and it is not dependent on any other thing. And it will guide other slave nodes. They will be having dependent degrees of freedom. Means, so they will take degrees of freedom from master node and interpolate as per the equation. So boundary conditions conflicting with slave node used in CERIG should not be applied to slave nodes. So if you want to constrain at this location, you cannot constrain on the slave nodes. You can constrain only in the mass elements. So CERIG simulate infinite stiffness. So one of the simple things, suppose the small example I can tell on this rigid region. Suppose I have a pipe here. So I want to apply a load at the center, but it's a hollow pipe. So what I can do is I can create a mass element, and this node will be master, and we will use CERIG or RB rigid region, and we will apply the load. Okay, or we can sorry. Suppose here I want to constrain. So instead of considering all the nodes here, what I can do is I will create here a mass element, and then we will create CERIG or rigid region, and we will constrain this node. Okay, so it will impose boundary condition in all other nodes. So this is one of the example of rigid region. We have many other examples why we need to use rigid region. So sometimes we can use simulate the bolt. So typically we have a bolt here. So when there is a bolt here, so what we'll do is we need not model complete bolt. We can model bolt by these elements. Okay, and then so at this location we use CERIG. So at this location, this beam element is here, and voltage will be resting here. So up to here, we will take the node, and we use CERIG to connect all the nodes on this plate. Similarly, at the bottom side also, we use same technique. So these are some examples. So rigid regions basically are used to impose some boundary conditions. Similarly, RB3 is a similar thing. Similarly, will used for it's a similar technique. Only thing is here master nodes are, so in CERIG degrees of freedom, slave master node is having independent degrees of freedom, and it will give directions to the all the slave nodes. Whereas in RBA3, slave nodes are these slave nodes will have independent degrees of freedom, and master node will be getting directions from all the slave nodes. So master node will be having dependent degrees of freedom. This is quite reverse compared to CERIG. So basically, RB3s are used to apply the loads. Okay, apply the loads on the component. So in the same example, if I want to apply a load here at the center, so here what we need to do is we need to create series and we can RB3, make a master element here and you can apply load here. So loads are applied using RB3 and boundary conditions are applied using CERIG. So in the master in RB3, you can apply a load, but you cannot apply a constraint equation constraints. The reason is it is not having a independent degrees of freedom. It is dependent on all the slave nodes. Forces, moments, mass on the master degree can be distributed to slave degrees of freedom. So one of the major advantage of RB3 is the force distribution. Suppose if I use a series here, if nodes are not evenly distributed, okay. So if I want to apply load like this, so you can use RB3 to try this one. If they are equispaced, load is equally divided. Okay, but here they are not equispaced, so there is a lot of gaps here. So this force distribution of RB3 ensures that the force distribution is distributed based on weightage factor of the location. So this is the major advantage. So always it is advised in stress analysis use RB3 for the load application, and you should not use CERIG for the load application. So RB3 creates constraint equations such that motion of the master is the average of the slaves. RB3 master node being an dependent node also has the implication that a load can be applied on it, but a constraint cannot. So force is distributed to the slave nodes proportional to the weightage factors. And some of the important information on constraint equations. Constraint equations can be major source of error in finite element methods. The improper constraint equation can artificially stiffen a model or induce the artificial stress risers. So we should be able to understand how. First of all, you should have a you should clearly understand what exactly is constraint equation. How, so when you use constraint equations, what can you do, what you should not do. Okay, so for CERIGs you cannot apply loads. For RB3 you cannot apply boundary condition constraints. So these things you should be able to understand. In most of the constraint equations should not be used in models undergoing large deflections. This is one of the important point. So when there is a component is undergoing large deflections, you should not use constraint equations. Okay. Constraint equation coefficients are usually based on original locations of the nodes, and the nodal displacement directions hence are not correct as the nodes move through large displacements. So the main reason is constraint equations are written based on original nodal locations. When there is a large displacement is happening, then the original locations will be changed, and these constraint equations are not valid. So this is very important. So when there is a large deflection, avoid constraint equations. Users should be very careful in constructing constraint equations when the nodal coordinate system has different orientation with each nodes involving in constraint. So we should be very careful while assigning constraint equations, and we should be clearly see whether nodal coordinate system, which nodal coordinate system we need to write this constraint equation. So this is very important, because based on this our results will change. So if you want to write constraint equations in a particular nodal coordinate systems, all nodes should be rotated before writing constraint equation. So this is one of the important check. So nodal coordinate system plays very vital role in constraints and couplings. Displacement relation described by the constraint equation is expressed in the nodal coordinate system. So basically the displacement relations we establish expressed in nodal coordinate system. So whatever nodal coordinate system nodes are assigned, that coordinate system only displacements will be assigned. So I think we discussed on the singularities, loads and boundary conditions at single point. For these things, yeah, the load. We'll discuss about the singularities, which is also important. Loads and boundary conditions at single point will cause artificial stress concentration. If you see here, there is a artificial stress concentration because we applied load only on single node. Uh, Another topic. So if you have questions, just let me know. Otherwise, we'll meet tomorrow at 10:50.